This is section 4.2b, where we will look at radioactive atoms and how they decay through a process called half-life. Remember that radioactive atoms or isotopes have an unstable nucleus, and they will release particles and or energy in order to stabilize. They do this through a characteristic rate called half-life. A half-life is the time required for half of the amount of the radioactive atoms to decay, to stabilize. The time ranges from seconds to even millions of years. So if we started with a sample size of 1 gram and we went through one half-life, the amount of material that would remain would be half of the original sample, which would be 0.5 grams. After 2 half-lives, there would be half of the half, or a quarter of the sample. And so you would see now that there is 0.25 grams. By looking at this graph, you can see that every time we reach the same amount of time, half of the original amount is disappearing. After the second half-life, you see it happen again, third half-life, and so forth. You can see that this is an exponential curve, and you can see that in theory, we can never actually get to zero. It just continually decreases. The material keeps on decreasing by 1/2. Believe it or not, there are a lot of common radioactive isotopes around you. Carbon-14 is used to date very, very old objects. Radon-222 is found in smoke detectors. Both uranium-235 and 238 are used in nuclear fusion. And iodine-131 happens to be a medical isotope that is used to destroy the thyroid gland in times where there might be overactive thyroidism or even cancer to the thyroid gland. Notice that each one has a distinctly different half-life, and each isotope goes through a different type of decay. For example, iodine-131 just goes through beta decay, and its half-life is every 8 days. So every 8 days, half the amount of the material will stabilize, leaving the other half to be still radioactive and to go through that process of decaying, whereas something like carbon-14 takes 5,730 years for half of the sample to disappear. Thus, it's a great isotope used to measure very, very old prehistoric type objects. In order to solve half-life calculations, there's a really important equation that you need to know. It is not on your reference sheet, and I am boxing it in right now. T, which stands for total time, divided by T1/2, which is the half-life time, is equal to the number of half-lives. The number of half-lives will be the number of cuts, or the number of times the sample will cut in half. There is a second, more algebraic equation that you could use that is also not found on your reference sheet, and you can see that in the red box. Amount remaining is equal to initial amount times half raised to the power of the number of half-lives. Both of these equations, once again, are not on your reference sheet, so you need to make a decision on which one you'd like to use. Most of the problems that you will do will be pretty simple, where you really don't need to do an algebraic equation, and so the first one will probably be your best choice. So let's take a look at our first example. We have 100 grams of radioactive carbon-14, and the half-life of carbon-14 is 5,730 years. We want to know how many grams would be left over after one half-life. In this type of question, the half-life time is not of importance here. We know that we're going through one half-life, and so if we originally start off with 100 grams and we cut it in half once, 50 grams would remain. If we went through 2 half-lives, then your 100, we cut a half into 50, and then cut in half again, leaving 25 grams behind. Another example, suppose you have 20 grams of sodium-24. Its half-life is 15 hours. How much is left after 60 hours? The fact that they've mentioned that the isotope is sodium-24 is just extra information. It will not be needed to solve this problem. You do find out that your half-life is 15 hours, so we're going to write T1/2 equals 15 hours. And the total time is 60 hours. So using our equation, T over T1/2 equals the number of half-lives. We'll find that 60 divided by 15 is going to give us 4 half-lives. Knowing that we were starting off with an initial amount of 20 grams, we will go ahead and cut that in half 4 times, excuse me. So 20 turns into 10, which turns into 5, 2.5 cuts in half, and you are left with 1.25 remaining. If you just want to plug it into the algebraic equation, amount remaining is equal to the initial amount, which is 20 grams, times 0.5 raised to the power of 4. You'll end up getting the same answer, 1.25 grams remaining. Another example, uranium-238 has a half-life of 4.46 times 10 to the 9th years. How long will it take for 7/8 of the sample to decay? Notice that the amount given to you is now in fractional form. We know that a whole is 8/8. So if I subtract 7/8 from 8/8, that will tell me that 1/8 will remain. So we're basically trying to figure out how many half-lives it will take in order for 1/8 to remain. Remember that the sample size is going to cut in half each time it goes through a half-live. So 8/8 becomes 4/8, and that is 1 half-life. 4/8 becomes 2/8, so that's another half-life. 2/8 becomes 1/8, and that's another half-life. So that means we went through a total of 3 half-lives. Since we know the total time, or we're looking for the total time, we know that the half-life time is 4.46 times 10 to the 9th years, and there are 3 half-lives. We can multiply these two numbers together, and you'll get your answer. 1.34 times 10 to the 10th years. An awfully long time. Another example, the half-life of radium-222 is 38 seconds. How many grams of a 12-gram sample are left after 114 seconds? So once again, we're going to go with our equation. T over T1 half is equal to the number of half-lives. You can see that the total time is 114 seconds, and the half-life time is 38 seconds. We're going to divide them. We end up getting 3 half-lives. We know that 12 grams was the original sample amount. We're going to cut that in half 3 times. So 12 turns into 6, 6 turns into 3, and 3 turns into 1.5 grams. Of course, remember that you can use the algebraic equation. We would take the starting sample size, and we would multiply it by 0.5 raised to the power of 3, and we would end up getting the same answer, 1.5 grams. Sometimes the only way to actually do these problems would be to actually use the algebraic equation, that the half-lives are not whole numbers, and so that disables that first approach. Let's take a look at this example. A sample of 3 times 10 to the 7th radon atoms are trapped in the basement that is sealed. The half-life of radon is 3.83 days. How many radon atoms are left after 33 days? So we know that 33 days is our total time. We're going to divide that by 3.83. That would be our T divided by our T1 half. That gives us the number of half-lives as not a whole number, but 8.616 half-lives. So we wouldn't be able to take that starting amount of 3 times 10 to the 7th and cut it in half 8.6 times. That would be very difficult to do. We could cut it 8 times or even 9 times, but not 8.6 times. So really the algebraic equation is the only way to do this. So we're going to take the initial amount, we're going to multiply that by 0.5, raised to 8.616, and that will give us our answer, which is 76,462 atoms remaining. Alright, there'll be lots of more practice in class. Just make sure you're comfortable with one or even both of those equations, And just remember that they are not on the reference sheet.